Hello there, welcome. This is your brand ambassador group in our element. We are here to take a look at our newly discovered alcohol synthesis. With this synthesis of ours, we have aimed to better the mouthwash you might use every day. Our ambassadors embarking on this new product are James Brown, Olivia Kindred, Hannah Schumann D, Justin Williams, and William Wooliver. We are the group in our element. Come along with us as we walk through the next Fresh Breath organic compound and show you this new compound that aims to improve the quality and capabilities of your mouthwash. Our group of creative ambassadors went on to create a beneficial marketing plan. This plan consisted of starting with the primary target audience, first finding who would benefit most and be most interested in a newer mouthwash, and then focusing on these people when advertising. In order to have a solid foundation with our interest of the new synthesized product, we would identify and research competition in order to improve advertisement and the quality of sales and product. We then decided it would be beneficial to advertise by creating and posting a social media tag and post to get attention for the product, all while establishing and finalizing a budget for our product. Within this marketing plan, we also thought it to be beneficial to ease the chemphobia around an alcohol-based mouthwash. Our compound is not like the others. We aim for our mouthwash to accomplish things like killing bacteria, preventing plaque, and maintaining tooth enamel, all while avoiding the harshness that so many people fear and want to avoid when using a mouthwash. Our product resembles a refreshing mouthwash with the help of an alcohol compound to enhance its beneficial capabilities for our users. This should entice people to buy our product because of the many superior attributes it has. The first compound was created by me, Olivia Kindred. This compound was given the name the Deca Double Alcohols. Right here are the two products that were formed following the 6-step synthesis. Although these products are not a real compound, I did decide to name them the Deca Double Alcohols. And you can see here that it's a carbon chain with an alcohol and a methyl. The IUPAC nomenclature names are right here. The top one is called 4-methyl-decan-6-ol. Decan-6-ol. The bottom one is 5-methyl-decanol-7-ol. The 6 steps of this synthesis were a radical bromination, elimination reaction, anti-Markovnikov addition, a carbon chain extension using alkylation, reduction reaction resulting in the cis product, and a hydroboration oxidation reaction to finish the synthesis and obtain an alcohol functional group. Now we move on to the entire synthesis. I first started with the alkene 2-methylpentane, shown here. I wanted to first halogenate it and did so by using the reagents Br2 and light. This was my radical bromination step. This gave me 2-bromo 2-methylpentane, as shown here. After this, with the 2-bromo 2-methylpentane, I decided to do an elimination step. This was more specifically an E2 reaction that used the reagents tert-butoxide and tert hydroxide as the solvent. This provided a major Hoffman product shown. The double bond is in the less substituted spot due to the use of a sterically hindered base, creating that double bond on the left side. The next step of the synthesis was the anti-Markovnikov addition step. This used the reagents HBr and the peroxides as the solvent in order to add a halogen, more specifically Br, and to replace the double bond on the less substituted spot and avoid creating another alkene. I then used the reagents sodium and carbon and a carbon chain containing 5 more carbons to create my carbon extension. This was an alkylation reaction, creating the extension in an alkyne, shown here. This was done by adding the alkyl group to the organic substrate molecule bromine. To then reduce the alkyne into an alkene, I used the reagents H2 and a Lindlar's catalyst as a reduction reaction. This created the cis version of the product, indicating that the major groups are on the same side of the carbon chain. and this is that product from that specific reaction. The final step of my synthesis is the most important. In order to add my desired alcohol functional group, I decided to do a hydroboration oxidation reaction. This reaction is the anti-Markovnikov addition of a hydroxyl group, or an alcohol, and a hydrogen in the place of the alkene. For my specific synthesis, I use the reagents BH3 and tetrahydrofuran. In the first step, and the hydrogen peroxide and sodium hydroxide in the second step. Because the compound contains a methyl, it produces two products, which are created here, or shown here, and as I discussed earlier. But you can see that we ended with our alcohol group on both of these products in the same methyl in the double carbon chain. We move on to the mechanism next. The mechanism I chose to elaborate on was the elimination reaction mechanism using the reagents terpetoxide and tetrahydroxide. Because it is an E2 reaction, the process is occurring all within one step, as listed here. The step being a proton transfer, the leaving group leaving, and the formation of the double bond. What is pictured here is the mechanism in the arrow showing the transfer of each of the electrons. Terpetoxide is sterically hindered, so the Hoffman product is favored and shown here. The first arrow here, which is supposed to point all the way to this hydrogen on the left side, is showing our base coming along to the beta carbon, or the most accessible hydrogen spot for our bulky base to attach to. It is on the left side of the molecule. In the same step, the protons from that hydrogen move onto the respective carbon bond to create the double bond, shown here by our second arrow, moving from this hydrogen to the carbon bond over here. Also happening simultaneously is the bromine leaving because of the bond breaking. And in order to maintain the possible amount of bonds, it needs to do this so that the center carbon only maintains the 4 bonds here. And it's indicated by this third arrow pointing to the bromine, indicating that it creates a leaving group for the bromine. There are 2 products that come from this reaction. The one shown, the E2 major Hoffman product, and the SN2 minor product, shown here. Although someone will discuss the uses of each compound, I would like to briefly go over the uses of my specific decadouble alcohols. This compound in our mouthwash is capable of killing an adequate proportion of bad bacteria, which improves most people's bad breath. It is also good at maintaining good bacteria, and is essential for maintaining the oral balance in many people's mouths. That is all for this compound. Thank you for listening and to this synthesis and of the decadouble alcohols provided by your group ambassador, Olivia Kindred. Have fun with the next one.